we are still talking about section 7.8 and dealing with compound interest. In this video, we're going to look at this compounding factor that shows up in our compound interest formula. So that part that is highlighted in yellow is the part that we're specifically going to be looking at. And we want to see what happens as n gets larger and larger. Right? Remember, n is the number of times being compounded. On this one, we're going to assume r is 1 just to make things a little bit more simple. So if we look at that and we have it compounded once, right, so our n is 1, then the value we get is 2. If it has 2 compounding periods, then it's 2.25. And as we keep going up and put numbers that are bigger and bigger and bigger in, we'll see when we put 100,000 in, we get 2.718268. Now that's starting to look like a number that we talked about earlier in this module, and that is E. Remember that we said E is approximately 2.72. And so as this n goes to infinity, as it gets larger and larger and larger, so we're dividing by a really large number, and then we're raising that power to a really large number, it's approaching E. And so we have another formula that we're going to talk about where we're using E in that formula. So the compound interest formula, where it's being continuously compounded, is given by the formula A of t equals P times E to the RT power. Again, A of t is that future value amount, P is our starting amount, R is our annual percentage rate, again written as a decimal, and T is the time in years. So the only thing that changes here is that our base that we're going to be using is E, that approximation of 2.72. Let's look at an example that illustrates that. A bank features a savings account that has an annual percentage rate of 5.7%, with interest compounded continuously. If Devin deposits $12,000 into the account, part A, how much will he have in the account in 7 years? So that formula for compounding continuously is A of t equals P times E to the RT power. We know that our interest rate is 5.7%, but we need to write that as a decimal before we put it into our equation. So again, moving that decimal 2 places to the left, we get 0.057. And then $12,000 is going to be our P. And now in part A, 7 years is going to be T. So let's put those values in and see how much money Devin will have in 7 years. So notice when we do that, we have A of 7, because it's talking about 7 years, equals 12,000 times E to the 0.057 times 7 power. So remember, on your calculator, there is an E button. Go ahead and find that E button, but you might want to multiply those two numbers together first so that you know what that is when you're putting it into your calculator. So when we multiply those together, I got 0.399 is going to be our exponent on E. So now in your calculator, put e to that power and then multiply it by 12,000. See what you come up with. $17,884. Remember that dollar sign is how much money Devin will have in the account in 7 years if it's compounded continuously. Now, what if it was compounded monthly instead? So if it's compounded monthly, we need to go back to that first equation, the compound interest formula. So let's use that. And remember that monthly is n equals 12. And the rest of the values will stay the same. So using the compound interest formula, we'll have a of 7 equals 12,000 times 1 plus 0.057, all raised to the 12 times 0.057 power. So let's put that in your calculator and see how much that's going to be. Now, do you expect it to be more or less than the amount that we have here when it's compounded continuously? I wonder how big of a difference it's going to make. Let's see. Did you think it was going to be less? I hope so, because compounded monthly is not compounded as many times as we're compounding continuously. But if we look at the amount, 17,884 compared to about 17,867, it really doesn't have that big of a difference between compounding monthly, which is usually what most accounts do, is compound monthly, or compound continuously.